Okay. The last thing I was doing this. It wasn't this one. It was with the workers. Um, Here it is. I was creating worker pools, and I was trying to implement it into my CLI where I print from a worker. So, let's just go over this again. So these workers. So in this scenario, the job is just a number, and the worker is just a number as well. I think I'm going to keep the worker as a number, so the ID remains a number, but then the job is going to be a channel with a string because it's just going to be job, the name. I don't know if I need to be passing. I think it's just going to be a string, right? So essentially, what I'm going to do that's differently is it's going to be the first command or the first parameter or argument in the CLI is going to be the amount of workers, and then the second one, or sorry, the first one is going to be what it's printing, and then the second one is how many workers. So it's going to be like if there's 5 workers, it's going to be like worker one starting word, worker one finished word, worker two starting word, worker two finished word. But it's going to be in like different orders because it's all going to run in concurrency. So this worker is just going to take in task, which is just going to be a string. And then I guess the results will stay a channel. Um, so we don't need this. Um, right. Yeah, because this has begun task. Um, task. Here, it's gonna be task. That makes sense. And then afterwards, we're creating the number of jobs, which we don't need because there's no number of jobs. Um, we don't need this. Um, sure, we can make result, but it's just going to be the size 1. Worker, which is going to act as the main. So results. Um, make and but of size 1, just because there's only going to be one task rather than the original 5 or jobs in their case. So here is where we create the workers. Okay, so for I 0, or we're going to want 1, I is less than or equal to worker count. Yeah. And then I plus plus, and then go func, I think is what they want. No, it's just go worker. That makes sense. Go worker. ID is going to be I, task name, and results. Results, yeah. There we go. So now that's going. And then the next thing I think we're going to want to do is just wait for results, right? Oh no, because it's not going to start yet until the jobs is filled. But in this case, okay, how are we going to make that work? Because it does, this starts up 3 workers, which we have, or X amount of workers, but it's not going to start them because there are no jobs yet. But we do have jobs because our job is just a string. Is that fine? That's fine. Then we just don't need this. And then we just need the results to empty the results to act as a wait group. So for yeah. What do we want to act? Yeah, because I guess the number of jobs is going to be work account A plus plus, and then results. That's it. So that should behave similarly. Print from. So let's just want. Well, let's say we do Golang tutorial, or just Golang, and then we'll have 5 workers doing it. Yeah, that looks like it worked. Oh, because did I simulate? Yeah, I did. Worker 1 started. Worker 1 finished job 1. Okay, so would it be different if I just X this out? Yeah, probably. Yeah, because I'm just gonna do 5 forward. Yeah, so that's what it would actually be in concurrency. But this just simulates a stronger task. Okay, this simulates task. This is to fill up our results channel so we can dump it to act as a wait group. So it'll only be able to dump once it's finished. That makes sense. So up here, create the results as a tally of what task is done so it can be emptied. Oh, so it can be emptied as a wait group. So here we start up the right number of Go routines. and we empty results when each task has been completed. This is this acts as a way to wait for the Go routines to finish before closing the application. So for pretty much this, so the Go routines, like if you let's say you finish your program, which is running like 5 Go routines, kind of like we could have done right here. What that's going to do is because they run in concurrency, it's going to go right to the end of file, and it's not going to end up running the Go routines, right? Because they're running it despite the fact that it's already gone below it on the code. So then what this does is this can only happen, this will wait. This like dumping this channel will wait for something to actually be inside the channel. And this will only have something inside of the channel to when this is done and this puts a value inside of the channel. So this kind of waits until, so even though the Go routines are acting all in concurrency here, this won't finish. It's like end of file until these are done. So it's a way to kind of, there's another way to do it with wait groups. I think I have one where I did learn how to do wait groups. No, I don't know. Maybe not, but yeah, wait groups are another way to do that. Okay, so this is what I was trying to do as a intro to atomic counters. This is what I was going to do last time too. The primary mechanism for managing state in Go is communication over channels. Make sense? We saw this, for example, with worker pools. Here are a few other options for managing state, though. Here we'll look at using sync automatic package for atomic counters accessed by multiple Go routines. Okay, I've never used the atomic package or the sync atomic package. We'll use an unsigned integer to represent our always positive counter. Okay, a uint represents not an integer, but a positive integer, I believe. Uint versus int. Yeah, unsigned integers only contain positive numbers. Um, a wait group, like I was just talking about, will help us wait for all Go routines to finish their work. So a Go routine kind of works similarly to what we had been doing with this, where we just put a value into results, because um, you can kind of fill up a Go routine, or sorry, a wait group. So like when you call this one, like when you create a new one, down here you can add one. So let's say, okay, this one's iterating through 50 times. So this wait group dot add is going to be called 50 times. So that means like this wait group is going to be this bucket that's full of like 50 different, I don't know if they're called instances or like values, I guess, 50 different things inside this wait group. And it's only going to finish the application until all 50 have been closed. So this wait group dot wait down here is going to wait until all 50 of them are closed. So here it looks like this is being ran in a Go routine. So while these are all running in concurrency, it's going to go down to this wait group, and this is what's going to be executed, or rather wait to be executed until all 50 have gone through this wait group dot done. The other way is just kind of like a bootlegged way to do it. Like this is like the proper way, but it acts the same in that like every time you kind of like open up this bucket, um, like it needs to be dumped. because here, essentially, it's just it needs to have a value. So you have to fill it with a value before it can be dumped. Um, okay, let's actually go through this now. So we just create a variable that's just a positive integer, and then we create a wait group, and then we're going to run 50 go routines that each increment the counter exactly 1,000 times. Okay, so to atomically increment the counter, we use add uint64, giving it the memory address of our ops counter with the address syntax. Okay, so for 1 and 50, we're running a go routine between 1 and between 0 and 1,000, where, okay, geez. Okay, this seems like it's like really, okay, so each iteration of this bigger for loop is adding 1,000 increments to our counter, but I don't get why we'd have to then iterate through this 1,000. Why don't we just add 1,000 and wait group that done? Wait until all the wait groups are done. Yeah, 50,000. It's safe to access ops now because we know no other Go routine is writing to it. Makes sense? Reading atomics safely while they are being updated is also possible using functions like atomic.load uint64. We expect to get exactly 50,000 operations. Had we used the non-atomic ops plus plus to increment the counter, we'd likely get a different number, changing between runs more because the go routines would interfere with each other. Moreover, we'd get data race failures when running with the brace flag. Next, we'll look at mutexes, another tool for managing state. Okay, I don't really get why this would do anything, but let's create something in our CLI. How could we do this? I guess the first parameter can be how many outside loops. Oh, it's too similar, right? If we did the outside loop being like the 50 for loop, and then the second parameter being the inner for loop. So it's like if you do print or like atomic incrementer 1010, it would be the counter would be 100. But that's too similar. Or whatever. Let's write it. Okay. Atomic incrementer. Okay. Var atomic incrementer. I'm gonna try to like look at the um, code example here on the left as little as I can. Okay, is equal to at cobra dot command. Yeah. Use just probably atomic incrementer. Sure, we'll do these later. I'm kind of talking about it enough to know. Actually, I'll do it long. Maybe I'll fill it in later. Run func command cover command r string. Okay, so from the other, I should do like error checking. I always forget to do that. So, um, oh, um, I'm just gonna go ahead and assume that we're gonna do atomic. Yeah, sure. Let's call it that. Um, tooling dot to int. see if it picks it up. There we go. Args 0, and then tooling, args. Okay, down here, atomic, I think I'm right. Outer limb int inner limb. And then here, do I want to do an error check where it's like it has to be, yeah, sure. U outer limb. Oh, sure. What? Yeah, I'll just, okay, is equal to U int 64 outer limb. If error not equal to no fmt dot current. Does that work? That doesn't look good. Oh, I want to do this. Var. I always forget the comma idiom. Comma idiom Golang. Maybe comma error. Comma error idiom Golang typecast. Let's see. Oh, okay. Yeah. Well, I'm an idiot. And then let's do the same thing with U inner limb. I'm gonna capitalize this. Inner limb. t dot print there. Oh, it's because I'm an idiot. Okay, how could we error check this? Would I want to do okay? No. Let's see, type casting in Go with error check. Okay, wait, let's see this. Hmm. Casting to uint in Go with error check. Maybe that's not called typecasting. This is not Golang. Let's see this. I know how to typecast, but I want to create an error check. Whatever. It might just work without. Alright, so I want to create the atomic counter, which is going to be var ops uint 64. And then I think I just iterate right through it, right? Yeah. For I is equal to 0, I is less than coverlen I plus plus, and then in here I run go. Close these. For y equal to 0, y is less than, right? Or arrow y plus plus. Okay. And then it was, I forget the package. Oh, I forgot the weight groups. Yeah. Um, var weight group is equal to sync dot weight group. And then here I'm adding wait group dot add one. Okay. And then here atomic dot add uint. It was an address to ops, and then it was the increment. Okay, yeah, so there is some problem. Oh, there we go, because that's a uint on the add. So I didn't have to typecast them because here it's just, yeah, that makes sense. Okay. And then here I need to do wait group dot done. Yeah. And then wait group dot wait. Yep, everything looks good. And down here was p dot num of operations. That seems relatively easy. Atomic incrementer 220. Oh, I'm an idiot. I need to add the initializer function. Root command, add command, atomic incrementer command. Hey, there we go. So I do wonder what this would look like if I do just plus plus it. Ops plus plus. Interesting. I didn't realize it would actually be that different. I'm gonna go ahead and put a little comparator. Ops atomic, and then ops reg uint 64. Ops reg plus plus, and then ops atomic, just to kind of done atomically. Ops atomic fmt.print and num of operations done regularly. Ops reg. Okay. There we go. Oh, whatever. I'll just add a little bit. Discrepancy saved by doing it atomic. Ops minus. I don't imagine there's a scenario where the ops regular does more, because it will never do more. I don't know why I guess it's just because the Go routines get in the way of each other. I don't know a scenario where this would actually be like super important. Like managing state. Give me like a bigger thing where I need to manage state. Let's just go on to the next one. I don't think I'm gonna go on too long with these kind of Go routine CLI. I kind of want to move towards something else eventually. Um, it could be another CLI tool that I probably should upload um, to GitHub. I wonder if I can just do it in here. Type version control. Create Git repository. Commit local changes. 8. Commit and push. First commit a little late. I never remember how to do this. I'm just gonna do it in the terminal. Create a GitHub repository. From CLI. What if I had it in my notes? Nope. Okay. Oh, it's because I had my notes not there. Okay, let's do this. First commit with a bunch of files. Git remote add origin. This one I'm going to call, just like I have it here, go routines CLI tool dot git git push view origin master. Could not read from a remote repository. Please make sure you have the correct access rights and the repository exists. We have to make it in GitHub first. Create a new repository. Go routines CLI tool public. Item. Okay, and there we go. Sweet. Fork. And then I can just go ahead and do it in a prettier way with fork in terms of just like updating and file open. Dope. That's in. Okay, now that that's public, people can go see that, I guess. Now let's do mutexes. I will be back though in just a bit.